What's up, guys? Last video we looked at the theory of energetics. This video we're going to start looking at some calculations, and specifically we're going to look at calorimetry. So most of the time the two examples we get of calorimetry are where we're burning something in a spirit burner, we're heating up water, we're measuring the temperature change. Or else we've got two reactants that we put in water, dissolve in water, and again we measure the temperature before and after. Okay, now once we have those values, once we have that experimental data, we then use these two equations. Q equals mc delta T and Q over N equals delta H. So here, Q is our energy change. And we measure that in joules. Mass, M, is our mass of substance heated. And hopefully you can guess that's going to be the mass of our water. Okay, generally speaking, we're going to be given the volume of water, but luckily there's a 1-to-1 ratio, right? So if we're given millilitres, 1 millilitre would be 1 gram, and 1 centimetre cubed would be the same as well. Okay, so if we're given our value in centimetres cubed or millilitres, it's just a very simple conversion to grams. C is specific heat capacity. Which we measure in joules per gram per mole, per Kelvin, sorry. And again, that's generally going to be the specific heat capacity of water, which is 4.18. We don't need to remember that, we're told it. And delta T is the change in temperature. Which is measured in kelvins, but because we're measuring a change in temperature, we don't need to do any conversions. And I'll explain that in our example. Now, delta H, which is going to be the sort of thing we're trying to work out in the end, is our enthalpy, or our enthalpy change. That delta just means change. And we measure that in kilojoules per mole. So hopefully you realise here we're working in joules, here we're working in kilojoules. And that's why often I'll do a little q over here and a big Q over here, so that I remember that I've got to convert this. This is in kilojoules. N is obviously our moles. Right? So let's get down to an example. Typical example, 0.6 grams of propane is completely burnt in air. Heat evolved raises the temperature of 50 centimetres cubed of water from 20 degrees centigrade to 84.9 degrees centigrade. Calculate the enthalpy of combustion, and we've got our specific heat capacity there. Right, so we've got our equation. Q equals mc delta T. M, we're told we've got 50 centimetres cubed of water. The mistake people will make is they'll use the 0.6 from propane. That's never going to be right. Okay, we're measuring the mass of the substance that is heated. And again, in our example here, it's the water that's heated. Again, if we're told 50 millilitres or 50 centimetres cubed with water, we know that's going to be 50 grams. C, we're told, is 4.18. And delta T, our change in temperature, is our 84.9 minus 20. That gets us to 64.9. Now we plug those values in and we get to 27130. 27,130, but remember that's in joules. On to our next step. So our next step, we're trying to work out our delta H. And again, that is Q over N. Q, here we need to do our change in units. We've got 27,130 divided by 1,000 gets us to 27.13. N, we've got our mass of propane. So again, if we think about a triangle, we've got mass, Mr. mole. So we need our mass equal to 0.6 mR is going to be, if we have our periodic tables, propane is C3H8. So I've got 3 lots of the 12 plus 8 lots of the 1 gets us to 44. So to work out my moles, I'm going to do mass divided by MR. Which gets us to 0.01364. Let me come back to here. 27.13 divided by 0.01364 which gets us to 1989. Now, the last thing we need to think about is, have we got an exothermic reaction or have we got an endothermic reaction? Now, there we just need to look, has our water heated up or has it cooled down? If it's heated up, energy must have exited our reaction and therefore our reaction is exothermic. If our temperature's gone down, it must be endothermic. Now here our temperature's gone up, so our reaction is exothermic, therefore we've got a negative value. All right, and again I can quickly flick back to what we did last time. Exothermic, our products have less energy than our reactants, therefore our value would be negative and our surroundings would have heated up, and that's in joules per mole. Okay, next one. So here, this would be our setup, okay? We've got 50 centimetres cubed of a hydrochloric acid, 50 centimetres cubed of NaOH. They're going to go in here, we'll measure the temperature at the start, and then we'll measure our final temperature at the end. So, again, Q equals MC delta T. M is equal to, we've got 50 added to 50. So there, that's going to be 100 grams. C is 4.18 again. Delta T, we've got our 26.8 minus 20. Now, we can even make a note to ourselves now. Here, our temperature's gone up, so we know that it's an exothermic reaction. So I might make a note to myself that I'm going to come back to this and have a negative value at the end. I can plug these values in and I get to 2842. Now, delta H equals capital Q over N. Q equals 2.842 because we've got to divide by 1,000. N. Now, remember, if you remember from last time, this is an enthalpy of neutralization. So we're thinking about 1 mole of water. So first of all, let's write a balanced equation for this. We have HCl plus NaOH makes H2O plus NaCl. Okay, does anything need to be balanced? 2 hydrogens, 2 hydrogens, 1 Cl, 1 Cl, 1 Na, 1 Na, 1 oxygen, 1 oxygen. Happy days, so that's good. I don't need to change these values. What I do need to work out is, have I got any of these in excess? So I need to work out the moles of both. So my N of HCl is equal to HCl 50 and 1. So here, remember, we've got CNV. So to work out my moles, I'm going to do my volume over 1,000 times by my concentration. And I've got 0.05 for NaOH. I've, funnily enough, got exactly the same thing. So I've got my 50 over 1,000 times by 1, 0.05. So actually, equal moles, 1-to-1 ratio, I use both, right? Now I put my values in. So I've got my 2.842 divided by 0.05. And there I get to 56.84. But remember, temperature went up, therefore it's an exothermic reaction. So I've got minus 56.84 kilojoules per mole. Great. So this is the question I'd like you to give a go. Have a little screenshot, give it a go. I'll answer it at the end of the next video. Now back onto what we did last time. So here, state the meaning of the term standard enthalpy of combustion. All that's asking for is our definition. And remember, we're always going to use this scaffolding when it comes to any enthalpy change. So when 1 mole of a compound is completely burnt in excess oxygen, in standard states, understanding conditions, perfect. That's going to be your 2 marks there, okay? Always remember this scaffold. This is our start, and we use it wherever possible. Now, here we have to label everything. A is our reactants, so it's hydrogen peroxide. B is our activation energy. C is our energy change. And D is our water plus oxygen. Bonus marks, XR endothermic. It is, of course, exothermic. And therefore, in our sort of calorimetry, so in this sort of setup, what would happen to the temperature of water? Yeah, temperature of the water would go up as it's an exothermic reaction. Remember, we'd have a negative value for our delta H there. Look, I hope that's helpful. Give the previous question a go. See you next time. Happy revising, guys. Please like and subscribe.